All right, hello everyone. Welcome to week 2 for maps, mapping, and geospatial technology. This week we're going to focus on the fundamentals of geographic information. With that said, I'm just going to go ahead and dive right in. So, consider this. Where are you? When someone asks this question, there is a wide variety of answers that you can give. For instance, someone asks you where you are and you're at Starbucks, telling them that you're at Starbucks is actually somewhat of a vague answer. Most towns are going to have multiple Starbucks locations. So, for instance, saying you're at the Starbucks next to Wegmans narrows it down, but maybe there are multiple Starbucks by Wegmans or, multiple locations that have a Starbucks near a Wegmans. So now think about it this way. If you have a medical emergency, first responders need to know your precise location so that they can find you and get you the help you need as quickly as possible. Simply saying that you're at Starbucks isn't going to suffice. You're going to need to provide much more of an exact location for them to find you. Oops. So geospatial technology has these issues, right? Geospatial technology deals with the same exact issues, and referencing and assigning location information to data being handled while also translating real world data from a 3D space to a 2D surface for examination. So how do we go from this right here to this over here? With that said, we use datums. So what is a datum? It is a reference surface or model of Earth that is used for plotting locations anywhere on the actual surface of the Earth. So there's horizontal datums and vertical datums. And a horizontal datum is a combination of a reference ellipsoid and accurately known control points on the Earth in degrees of latitude and longitude. There's also vertical datums, which are heights above or below the surface. So this is a vertical datum, which is on the top of Mount Whitney. It's the marker at the summit of the mountain that tells you the altitude of the highest point of that mountain. So what's a reference ellipsoid? It's a mathematical approximation of Earth's shape. As I'm sure everyone knows, Earth is not a perfect sphere. The same spot on the surface, the same spot on one, wait. The same spot on the surface gives you a different value for different ellipsoids. So the Earth, Earth is an ellipsoid, which basically just means it's larger at its center than it is at its poles. If you were to squeeze the top and bottom of a basketball to compress it slightly, you'd have a basic spheroid shape. However, since Earth isn't perfectly smooth for the ellipsoid, gravitational forces affect different parts of Earth in different ways, causing some areas to be out of sync with the ellipsoid. This is a diagram from the textbook for how the Earth approximately looks, given the fact that it's an ellipsoid. For datums, there are a couple different datums you guys will need to know. So there's the NAD 27, which is based on the Clark 1866 reference ellipsoid, NAD 83, which is based on the North American datum, and is based on the 1980 geodetic reference system ellipsoid. And then there's WGS 84, which is the World Geodetic System of 1984. And then there's also datum transformations, which are they're a way to alter the measurements from one datum to another. So now let's move on to coordinate systems. So we have coordinate systems. There's plane coordinates, which are X and Y or lat and long, depending on your projection system, which I will talk a little bit more about later. And plane coordinates are used because surveyors are concerned with accurate measurements. Plane coordinates are also based on projects and contain some level of error, which brings up the question of why do we use them if they're inaccurate? So we do use them because feet and meters aren't nearly as accurate as degrees, minutes, and seconds, which also is how the Earth is divided. It's divided into 360 degrees. Each degree is divided into 60 minutes, and each minute is divided into 60 seconds. So geographic coordinate systems, GCS, it defines where the data is located on the Earth's surface. A GCS is round and records locations in angular units, which is usually degrees. And since every point can be measured using the same datum, the shortest distance between 2 points is referred to as the great circle distance. The GCS is Global Reference System, as I just mentioned. And then these GCSs will consist of lines of latitude and longitude that cover the entire planet and are used to find a specific position. So in the image we have here, that green dot is at 40 west and 40 north for degrees. So then there's also lines of latitude which run from east to west in a east to west direction around the globe, with the equator serving as the starting point of 0. And then we also have lines of longitude which run from north to south, from the North Pole to the South Pole, and the prime meridian is that starting point of 0. And then the latitude and longitude are measured in degrees, which is the unit that can be broken into 60 subsections for each minute. There's 60 minutes in a degree. The latitude and longitude system of geographic coordinate systems also serves for the basis of the several different time zones across the Earth. Time zones set up the concept of a 24-hour day, with each zone having a different time as it relates to the current time in Greenwich, England. This is where everything is based off of, which is this line right here, or this zone right here, as you can follow it right here. So then Earth is spanned by 360 degrees of longitude, and there are 24 hours in a day, which means that for every 15 degrees, there is a new time zone. The prime meridian marks the start of a new time zone, meridian marks... No, I had that right the first time. The prime meridian marks the start of a new time zone, and the international date line marks the division between 24-hour time periods, and the division between one day and another. So on to map projections. What are map projections? Map projections are a way to represent the 3D surface of the Earth on a 2D surface, and it converts lat and long coordinates into planar Cartesian coordinates, which are X and Y. Map projections, the exact definition is the translation of locations on a 3-dimensional Earth to a 2-dimensional surface. Web Mercator is an example of a map projection and is widely used and was adopted by Google Maps in 2005. And then we must also realize that such representations will always have some sort of distortions built into them, simply because they're 2D versions of a 3D reality. The shapes of objects, the sizes of objects, and the distances between objects or the directions of objects will usually be distorted because of this projection. Some map projections may retain the shapes of continents but misrepresent their land areas. Other projections may present the land areas accurately but throw the shapes out of place. So what are some properties of map projections? Process of flattening the Earth is going to cause distortion in one or more of the following spatial properties, those being distance, area, shape, and direction. And then when a flat map is made, choices are made depending on the intended use of the map as to which of these properties the map creators want to preserve. And no projection can preserve all of these properties. So there's always going to be some sort of distortion to, some degree. Some will have it worse than others. But again, it all comes down to what the intended use of the map actually is. Projections are basically just a mathematical transformation. Can be broken down into a formula. So points, lines, polygons on a curved surface of the Earth must be rendered onto a flat map surface. And different projections will use different values and transformations to render those features. Basically, they're all just being broken down into different formulas and how to actually project them onto this flat map, basically from our 3D globe. Which then brings us to projected coordinate systems, or PCS. It tells the data how to draw on a flat surface. Locations are usually recorded in linear units, this being meters. So there's three common projection surfaces. So there's cylinder, which is the cylindrical projection. There's the plane or planar projection, and then the cone or conic projection. Imagine this when you go to imagine a globe, and imagine that it's translucent. And there is a light bulb in the center of it. So if you turn that light bulb on, it's going to project everything that's on the globe onto the wall, essentially. And the imaginary light will cast shadows onto the walls for the shapes of the continents. So as you might imagine, the appearance of the projected grid will change quite a lot depending on the type of surface it is projected onto, and how that surface is aligned with the globe. The three surfaces that you guys can see in the slides right here, the plane, cone, and cylinder represent categories that account for the majority of projection equations that are encoded in GIS software. All three are shown in their normal aspects. The plane often is centered upon a pole. The cone is typically aligned with the globe such that its line of contact coincides with a parallel in the mid-latitudes. And the cylinder is frequently positioned tangent to the equator unless it's rotated 90 degrees. And the following illustrations show the projected graticals produced by the projection equations in each category. So these are the different types of projections, the most common ones. As you can see in this image, this is that light bulb example I gave in the last slide. For cylindrical projections, equations yield projected graticals with the straight meridians and parallels that intersect at right angles. The example shown in this top corner right here is a cylindrical equidistant in its normal equilateral aspect. As for the second one, the conic one, conic projections yield straight meridians that converge towards a single point at the poles, parallel that form concentric arcs. And the example shown in the center is the result of an Albers conic equal area, which is frequently used for thematic mapping of mid-latitude regions. And then this last one in the bottom, planar projections also yield meridians that are straight and converge, but parallels form concentric circles rather than arcs. Planar projections are also called azimuthal because every planar projection preserves the property of azimuthality. The projected gratical shown above at bottom right, on the bottom, is the result of an azimuthal equidistant projection in its normal polar aspect. Appearances can be deceiving. It's important to remember that the look of the projected gratical depends on several projection parameters, including latitude of projection origin, central meridian, standard lines, and others. Customized map projections may look entirely different from the archetypes described above. So, conformal versus equal area. Conformal is the scales of the projection in the x and y directions. They're always equal. And it's useful for navigation because a straight line drawn on the map has a constant bearing. Conformal shapes are maintained, sizes are incorrect, whereas equal area shapes are distorted, but the sizes are correct. An example of this translation of the world into two dimensions is the Mercator projection that you guys can see. That you guys can see here in Figure 2-10. And it was a map developed in 1569 by Flemish cartographer Gerardus Mercator for use as a navigation aid. It was designed so that every straight line on the map was a line of constant direction. The Mercator projection encompasses the whole globe, and although it keeps the shapes of areas intact, the sizes are very distorted, and they become more distorted the further away you go from the equator. So, for example, take a look at Greenland and Africa. They look to be about the same size, and they're not. Africa is just about 13 times larger than Greenland, as you can see represented in the equal area map projection right here. So Universal Transverse Mercator, or UTM, is a grid system that works by dividing the world into a series of zones and then determining the x and y coordinates for a location in that zone. The UTM grid is set up by translating real-world locations to where their corresponding places would be on a two-dimensional surface. But UTM only covers the Earth between 84 degrees north and 80 degrees south. Okay. So, Universal Transverse Mercator has a couple of characteristics for each individual UTM zone. The equator is going to be at 0 meters north for the north zone, and then the central meridian is easting of 500,000 meters east. And then each UTM coordinate is going to be made up of a couple of different individual characteristics. First one's going to be the zone number. this is just what zone it is on the map. And then it's followed by whether or not it's in the north or the south hemisphere, which is just represented by an N or an S. That is then followed by the 6-digit easting coordinate, and then that's followed by the 7-digit northing coordinate. Here's an example, and then we can actually see in an image of what it would look like on a or in an actual zone. And I actually have a zone pulled up that we can go ahead and take a look at. So as you can see, I have the North Hemisphere followed by zone 18, and then the 500 for the East, and the 500,000 for the East, and the 5 million for the North. And it is just outside of Cornwall. I believe that is in Canada. Yeah, Cornwall, Canada. So the U.S. isn't perfect. The UTM zones don't line up perfectly with the states, leading to many different states being divided. New York's one of them. Pennsylvania's one of them. North Carolina's one of them. California, Oregon, and Washington, a bunch of different states are divided. So this leads us to the state plane coordinate system, which is made up of 122 different zones. It's another grid-based system for measuring and determining coordinates. It was designed in the 1930s before the advent of computers. Today, it is used as a coordinate system for U.S. data, especially city and county data, and measurements. It's a projected coordinate system that uses a translation method similar to UTM to set up a grid coordinate system to cover the U.S. It was originally measured using the NAD27 datum and is now using the NAD83 datum. So a little more on state plane coordinate systems. Unlike UTM zones, which follow the lines of longitude, state plane coordinate systems are formed by following state or county boundaries. And a state is often divided into multiple zones. For example, Ohio has 2 zones. Nevada has 3. Nevada West, Nevada Central, Nevada East. Texas has 5. California has 6. While all of Montana is represented by a single zone. To determine the coordinate system, or the coordinates for a point in the state plane coordinate system, you must first know which state the point is in, and then you must identify the zone within that state. For example, to map data from Miami, the state is Florida and the zone is Florida East, while Cleveland is in the state of Ohio and is in the Ohio North zone. This is how New York is divided up for its state plane coordinate system. And that is my last slide. So there's going to be a second video following this one. We're going to go through our first little lesson in ArcGIS Pro. I'm going to do a walkthrough. It is going to go through the second assignment, well, I guess technically the third assignment. Definitely check that one out. It's going to go through the whole assignment. There might be 1, maybe 2 questions that you'll have to do on your own. But it will be a part of the assignment, so definitely make sure you watch that lecture. And I will see you guys in the next one.